As an example, let's work out the algebraic or discrete equation for mass conservation for one particular cell. And I'll pick this cell. And I want to know what the volume of flow crossing each of these faces is. So I have 4 contribution to the volume of flow. And I'll set that to 0 because a net volume flow out of the cell has to be 0 for mass conservation. Mass and volume are equivalent in compressible flow because they're just different by a constant, the density. Let's focus on this phase first and assume that the average value of velocity at that phase is equal to the value at the midpoint that's shown by the cross. And that's an approximation. Let me say that cell 1 and that's cell 2. So the volume flow rate, so that's a volume of flow and that's a rate, so that's per unit time. For the phase that's between cell 1 and 2, and I'm indicating, I'm using this symbol for volume to distinguish it from V for velocity so that you don't get confused between V for velocity and V for volume. That's equal to the velocity at the green cross, which I will denote as U1-2. And velocity times the area of the phase will give us the volume flow rate. Let's say this distance is delta y. That's called a mesh spacing. This means that the area of the right face is going to be delta y times 1, and that is the dimension in the direction perpendicular to the screen. And this term will drop out of, it will be common to all the terms and will drop out. So we can assume 1 without the loss of generality. And there is an error when we write that down because we have assumed that the value that this velocity value here is equal to the average for the phase, which is an approximation. We will quantify the errors or get a better idea of the errors a little bit later on when we talk about the order of accuracy. Now this velocity here I'm not calculating directly. So I'm going to use that in term as an average between that value, and those are values I'm going to calculate directly. So U12 I will say is the average of U1 plus U2 divided by 2, and we'll assume uniform spacing for simplicity, uniform grid spacing. And in that process we introduce another error. So that's a different error, and there are 2 different errors coming in. Now I can use this term and put it back in here, and the volume of the volume flow rate through that phase becomes U1 plus U2 divided by 2 times delta y, and I won't write that 1 over there. And there are 2 errors involved in that approximation, as we just talked about. And what I'm doing is, in the process, I'm doing that, the integral. If I did the integral form of the mass conservation, I would, that's a contribution to that integral from that phase. So I can do this based on the integral form of mass conservation or from physical arguments, and the physical arguments are a little bit easier to understand, so I'm just doing it based on the physical arguments with the understanding that the 2 are equivalent. Similarly, to calculate the volume of flow going through that boundary, I'll have to interpolate between the velocity over here and the velocity over here, and let's say that's cell 3. So I'll have to interpolate between, cell 1 and cell 3, particularly the v velocity, that is a velocity in the y direction. I'll let you work that out. And then the contribution from the top boundary is going to be 0, and the contribution from the left boundary is going to be known because we know the velocity coming in from the boundary conditions. So if you put it all together, we will get an equation that so the volume of flow from the right face will involve some coefficient times u1 plus some coefficient times u2. Then from the bottom face, I will get some coefficient times v1 and some coefficient times v3. There's no contribution from the top face, and from the left face I will have a constant value, so that'll just come to the right. And this is the algebraic equation for mass conservation, and I'll let you work out what the coefficients are in the exercises.